Okay, so let's talk about voltaic cells. Voltaic cells are also known as galvanic cells, and essentially they are devices which generate current. So a battery is a galvanic cell. A galvanic cell will contain a spontaneous redox reaction that generates electricity. So we take chemical energy from the redox reaction and convert that into electrical energy. So we've been writing half reactions and balancing redox reactions. And those half reactions that we write are what are going to show up in these, each cell of a galvanic cell or a voltaic cell. So in this figure, we have a zinc reaction taking place on the left and a copper reaction taking place on the right. And in this type of galvanic cell, they are very explicitly separated. And so it's really easy to see those two chambers. I feel a little better. So for instance, we are going to have on the left zinc solid, which is this metal rod, oxidizing to form zinc ion, which is in solution. So this would be a solution of zinc chloride, and we'd be producing more zinc ion. In the other side, we're going to have a copper wire or a copper plate here in a copper solution. And that's where reduction is going to occur. Okay, reduction because the copper is gaining electrons, and oxidation for the zinc because it's losing electrons. So if we look at a voltaic cell sort of as a diagram, and I assume you looked at these a little bit in recitation yesterday, sort of ahead of schedule, but I wanted you to have those questions for the exam. So let's take a look at what's happening at the molecular ionic level. So we're going to have our zinc half reaction where oxidation is taking place. We know it's oxidation because electrons are on the product side. And we're going to have our half reaction where reduction is taking place. This is with the copper, and we see that we are gaining electrons as a reactant. Okay? So we have our zinc rod. The zinc rod is connected with wires, so some electronics wiring here to the copper solid electrode. We have a zinc solution that the zinc solid is placed into, and a copper solution that the copper rod is placed into. And we also have a salt bridge. So a salt bridge is going to contain ions that are not involved in the redox reaction. So in this case, we have a sodium nitrate salt, which completely dissociates into sodium ion and nitrate ion. And the salt bridge allows for electrons to flow. If we didn't have this salt bridge, we would have electrons flow from the anion to the cation only momentarily, and then they would stop because we would have a buildup of charge. Okay? So because we have this salt bridge, it allows for this cycle of charge to move. Okay? So an important thing to note here is that electrons flow from the anion to the cation. Okay. And almost always we write the draw the anode on the left and the cathode on the right. Another sort of mnemonic here that is really useful is that oxidation occurs at the cathode. Oh, sorry. Oxidation occurs at the anode. Got ahead in my brain here. And ox, that's a little mnemonic for this one. And then reduction occurs at the cathode. So you might see red cat as that mnemonic. Okay. Oxidation at the anode, reduction at the cathode. Okay, so let's think about this oxidation reaction taking place with the zinc. All right, so we're going to take our zinc solid, and it's going to become oxidized. So we're producing zinc ion. That zinc ion goes into solution. So in this diagram that's showing the atoms, we have our zinc atom forming the ion, and it enters into solution. And it's going to migrate towards the salt bridge, that positive charge migrating towards the negative charge of the nitrate. Now, this sodium and nitrate is dispersed all throughout. It's not just sodium ions on one side and nitrate on the other. But what this is trying to show you is that the nitrate ions are going to migrate towards the solution with the positive charge, and the sodium ions are going to migrate towards the side where the electrons are headed. Okay, so electrons are moving away, so we need our negative charge of our nitrate to move towards that direction, and the electrons are coming into the copper, and that makes it so we need to have this positive charge balance. Okay. So, okay, we've got our electrons moving away from the anode. They move towards the cathode. At the cathode, the copper ions in solution are going to react with electrons to form copper solid, and that's going to collect on this copper rod. And so eventually what you would see, and I don't know if I have the right figure, is that there would be some amount of zinc that is sort of deteriorating from that rod. Eventually it would sort of all go away, and they would see a buildup of material on the copper. Okay. This is, in some respects, how electroplating works. Okay, so you're able to put a thin layer of metal on another piece of metal through the process very similar to this. Okay. Questions on this type of galvanic cell? I'm going to leave this slide. Make sure you can figure out what is happening at the anode, what's happening at the cathode, and why the salt bridge is important. Okay, I'll leave that to you all to write in your own words. So let's look at a redox reaction that is spontaneous at room temperature. We want to figure out what half reactions are happening, and then from there determine which half reaction occurs at the anode and which occurs at the cathode. So here's our redox reaction that we're going to work with. We have a dichromate combining with H+ and iodide to form chromium ion, iodine, and water. So let's take a couple minutes and try to write out the half reactions. So starting sort of along the process that we did when we were balancing our redox reactions, work through that to get to the balanced half reactions. So that's before we recombine them again with canceling out electrons. All right, so hopefully you got started at least. I'm going to split up this reaction and separate the chromium. So we're going to have Cr2O7 2 minus forms 2 Cr3 plus. And I'm going to also include a second half reaction for the iodine, or iodide to iodine. So I'll have 6I minus forming 3I2. I'm going to leave off my phases. I don't know where to put the hydrogen ion and the water. Okay, so I'm not going to worry about that right now, but what I'm going to do is start balancing these half reactions. Okay, we're going to start here and then work through what we did last time. So let's work with the chromium half reaction. We'll make sure that our chromium is balanced, which it is. We have 2 chromium on both sides of the arrow. Then we're going to balance for oxygen using water. And so I have 7 oxygen on the reactant side, so I need to add 7 water to the product side, and there's our 7 water. Okay, that's good, promising. And because I added 7 waters to the product side, that's 14 hydrogen. I need to add that to the reactant side to balance that. Okay. And while we're here, let's go ahead and figure out the number of electrons that we need to add to balance out this half reaction. We have a total of 14 positive ions minus 2 with our dichromate, so a total of plus 12 in terms of charge on the reactant side, and a total of plus 6 on the product side, so 2 times the positive 3. And so we can add some electrons to balance that out. If we add 6 electrons to the reactant side, that brings our total charge to plus 6, which is equal to what's on the product side. Everyone okay with that? Okay. For the iodine half reaction, our iodine are balanced, 6 on both sides of the arrow. And we don't have anything else to balance. So the only thing other than electrons. So we're left with balancing electrons. We have a total of minus 6 on the reactant side. So we can add 6 electrons on the product side. Now, because we have balanced redox reactions and we have electrons where they should be, we can see where reduction is happening and where oxidation is happening. Okay? So because reduction is gain of electrons, this half reaction is the reduction half reaction. I always write this out because I'm easily confused by these. It's just jumbled up in my brain. But if I say reduction is gain, and then red cat for reduction occurs at the cathode, I can tell you then that that is the reaction that's going to occur at the cathode. Our other half reaction, this is oxidation. We lose electrons, and we have anox. Oxidation occurs at the anode. Okay. All right, questions on that? Okay. All right, so why do we really care about any of this? So we can harness the power of redox reactions and use them in things like batteries, which are obviously incredibly important in our lives and hopefully becoming more important. It's made more sense a few days ago. With the increased use of solar energy, but that might not happen anymore. Anyway, we need batteries. Cell potential. So a set potential is basically like a potential in terms of energy. So if we think about a waterfall with high potential energy at the top, low potential energy at the bottom, that's essentially what we have in a redox reaction. At the anode, we have high potential energy. You can think about having an electron density there, going to low potential energy, and the electrons flow from the anode to the cathode. Okay. Now, our ability, so here's like a light bulb being turned on by this battery. Our ability to use that energy is dependent on the materials that we use to make that battery or whatever it might be. So we need to be able to calculate the amount of energy that we can produce using particular half reactions. And so we are going to figure out how to calculate what we call the cell potential. And we'll be typically thinking about standard cell potential, so under standard conditions. 25 degrees Celsius, 1 atmosphere, and 1 molar solutions. So in order to calculate the cell potential, E cell, we use standard reduction potentials for half reactions. So we think about our half reactions. We always write them as reduction reactions, and then we can have a value, a voltage associated with that reduction reaction. So these reduction potentials are values you can look up on a table. You're not expected to memorize these, okay? But if you have a table, you should be able to say, okay, this has a higher reduction potential, and that means this in terms of reaction, but we'll get to that. And this is another one of these, just like the Henderson-Hasselbalch, I told you not to bother looking it up online because there was one with PKB and switching. Same with cell potential, all right? Use this version for cell potential. We're going to use reduction potentials. We're going to take the reduction potential of the reaction that occurs at the cathode minus the reduction potential of the reaction that occurs at the anode, okay? These reduction potentials are essentially a relative value. We have a reference value where we reduce H plus to H2. Okay, and that has a value of 0 volts, and everything else is relative to that. This is an important statement here. For a voltaic cell to work, or galvanic cell to work, it must have a positive value for the cell potential. Okay? So when you're looking at these problems and you know that you're working with a galvanic cell or a voltaic cell, you know the cell potential has to be 0, or has to be positive. And the reason is what we'll show you after the material for this exam, but we can relate that to the Gibbs free energy, and it allows for us to make a prediction on whether the reaction will occur. Okay. I'll just write it out because it's useful to see. So this is the relationship with the Gibbs free energy. Delta G equals minus NF E cell. So if our cell potential is positive, delta G is negative, and the reaction is spontaneous. Okay. So that is why we're going to be focusing on having a positive cell potential. That's for next exam. The final exam. Whoop. Okay, we're going to look at another voltaic cell. This one has zinc at the anode, but now has the hydrogen half reaction at the cathode. And we can look up the values for these reduction potentials. Let me find where my notes are. So for the zinc reduction reaction. So this is the reduction as, this. For the zinc reduction reaction, okay, the reduction potential minus 0.76 volts. Okay. Notice I switched the reaction here. This is the reduction potential for that reduction reaction. Okay? That's what we want for our E-cell equation. All right. For the hydrogen reaction, this is reduction as written. And so the reduction potential is, like I said before, 0 volts. And so if you were told that this was a galvanic cell, but you weren't sure what was the cathode and which was the anode half reaction, you could actually just move the numbers around, manipulate the numbers to figure out how you get a positive cell potential. And that will tell you where the cathode is, or which reaction is the cathode and which is the anode. For this reaction, we know that the zinc half reaction is at the anode, and the hydrogen is at the cathode. And so when we calculate the E cell, we were going to take that at the cathode for the hydrogen, which is 0 volts, minus that at the anode, negative 0.76 volts, and we'll end up with a cell potential of 0.76 volts, which is what is being shown here on the voltmeter. That's the maximum voltage that we can get from this galvanic cell. Now, if we weren't sure which was the anode and which was the cathode, and we reverse those numbers, we would have minus 0.76 minus 0, and we would end up with a negative cell potential, and we know that that will not work for a galvanic. So that is one way that you can sort of numerically figure out what's happening in a galvanic cell. Does that make sense? If we look back at the zinc and copper galvanic cell that we looked at before and calculated the cell potential, again, we need to look up the reduction potentials for our zinc and copper half reactions. Again, the zinc 2 plus 2 electrons forming zinc solid, has a reduction potential of negative 0.76 volts. The copper 2 plus 2 electron forming copper solid, has a reduction potential of 0.34 volts, okay, positive value. And so when we calculate the cell potential, take the reduction potential at the cathode minus the reduction potential at the anode, so I'll have 0.34 minus negative 0.76, and we'll get 1.10 volts. Okay, so positive E cell means it's a spontaneous reaction, which it must be if we've called it a galvanic cell. Okay. And again, that's sort of what is showing here on the voltmeter. That's the amount of volts we could get out of that galvanic cell. All right, questions on that? Yes?
Is there like potential that on an exam they would like make it so the anode wasn't on the left side? Is there a case of the other side?
On the drawing?
Yeah.
So electrochemists have a convention of drawing like this. If it's done, but not, that is in the US. It actually varies by country. Some of them are reversed. So if we flip them, where you found some resource somewhere else, my answer is we should always draw it like this, because it's confusing when we start mixing things up. So I'm going to say the anode is always in general.
Okay, thank you.
That's a really complicated answer for what you wanted to know, but that's the case. Electrochemical convention is infuriating. Okay, other questions? All right. Okay, so we looked at this these half reactions for the dichromate and iodine reactions, half reactions. So for our reduction reaction, we had Cr2O7 2- plus 14H plus and 6 electrons, forming 2 chromium 3 plus and 7 water. We're going to calculate the cell potential for these. We already determined that the reduction reaction was the chromium half reaction and the oxidation is the iodine containing half reaction. I will tell you that the reduction potential oh, I did a terrible job of writing this in my notes. The reduction potential for the chromium reaction is 1.33 volts, and the reduction potential for 3I2 plus 6 electron forming 6I minus is 0.54 volts. So with those two values, so we had to look that up on a table, okay? Looked up our reduction reactions. Given those two values, what is the cell potential? Okay, so we know that the reduction reaction is the chromium half reaction, so we're going to have 1.33 volts minus that at the oxidation at the anode, which was 0.54. And we get 0.79 volts. Now, what I want to point out here, and I think it's even more obvious in this example than it was in others, is that this value is not dependent on any of the stoichiometries, right? I have 6 electrons being transferred here, right? But the stoichiometry is unimportant in terms of the potential. So you don't need to worry about multiplying these reduction potentials by any factors. It is not dependent on stoichiometry. And I think that is counter to almost everything we've seen so far this semester. So I wanted to point that out. Okay. Questions on that? Okay, so I mentioned you don't need to memorize reduction potentials for various half reactions, but you do need to know the trends, and you need to know how to interpret a table of reduction potentials. So, for instance, if the more positive the value of the reduction potential, the greater it is the better it is at reducing. Okay, the greater the tendency for reduction under standard conditions. The strongest oxidizers. Okay, remember that term. Oxidizers is the same as oxidizing agent. And those are reduced. They have the most positive values for reduction potentials. And the strongest reducers, or reducing agents, they are oxidized. They have the most negative reduction potentials. At a table, probably a little hard to see. I'm going to sort of zoom in here at the top. At the top, we're going to have our most positive values for the reduction potential. For instance, for the reduction reaction of fluorine plus 2 electrons forming 2 fluoride, the reduction potential is 2.87. This is a very easy reduction reaction to take place. That means that F2 is a strong oxidizing agent. F minus, on the other hand, is very difficult to oxidize. It is the weakest reducing agent. At the bottom of the table, these are our most negative values of reduction potential. So for lithium ion plus an electron forming lithium solid, the reduction potential is minus 3.05 volts. The lithium ion is most difficult to reduce. The lithium solid is easiest to oxidize. Okay, so looking at both sides of the reaction, think about what is easy or hard to reduce and what is easy or hard to oxidize. And they're opposites. Okay? So if you're given some reduction potentials for a couple of reactions, make sure you can predict what is easier to reduce, what is easier to oxidize. Okay, so remember how I told you that you could take 2 half reactions and calculate a cell potential for a galvanic cell without knowing what is oxidation and what is reduction? You could do that with this. I am giving you the redox reaction, but you could do it without knowing that. So I'll give you a couple minutes here to calculate the cell potential for this reaction. All right, so our E cell is the reduction potential at the cathode minus the reduction potential at the anode, and it must be a positive value because we have a galvanic cell. Okay. So really, if we're basing just on that, the only way mathematically that works out is that if the aluminum is where the reduction is taking place, so we'll have minus 1.66 volts minus the negative 2.37 volts for the magnesium, and we'll get 0.71 volts. The other way that you can see what is happening is with the redox reaction. So we have the aluminum ion on the reactant side. It's going to gain electrons to form the aluminum solid on the product side. The magnesium solid is on the reactant side. It has to lose electrons in order to form the ion on the product. So both of those ways can lead you to the right answer. I just wanted you to see that. All right, that's the end of